Yay! Now I get to learn about ionic crystals. I remember crystals was that pattern of positive and negative. That was from the last reading. And ionic is one of the types of bonds. Alright, so it says chemists have studied reactions of unstable atoms on the periodic table for hundreds of years. One of the first types of reactions to be observed was the reaction between metals and nonmetals, which I guess is ionic. When a metal is brought into contact with a nonmetal, there's often a flaming or explosive reaction. Ooh. That is exciting and sometimes dangerous, probably always. When a metal reacts with a nonmetal, an ionic crystal is always produced. So produced means gotten. The most well-known example is ordinary table salt or sodium chloride, which is produced when sodium metal is exposed to chlorine gas. So sodium, that's a metal, right? And then chlorine gas, that would be the nonmetal. Okay, so let's look at this figure. This is highly magnified images of sodium chloride salt crystals. So there's these little crystals, I guess, and oh, I guess this is what it looks like. So this is the positive-negative pattern. It says the sodium cation Na+ is held in place next to chloride anion Cl- by electrostatic attraction. That sounds important. This does not conduct electricity because the cations and anions cannot move. Right? So I know sodium, since a cation, it's lost an electron. It's going to be smaller. So the purple one must be sodium, and then the green one must be chlorine. So we've got positive, negative, positive, negative. It's interesting about this is that it's three-dimensional. Ooh, this is so awesome. Okay, dissolved sodium chloride. So dissolved, I know that means you put it in water, right? Like when you're making, lemonade or Kool-Aid or Gatorade from a powder. When dissolved in water, the crystal dissociates. Okay, I'm not 100% what dissociate means into cation and anion. But from the drawing, it looks like it means break. Right, because they're no longer together. This conducts electricity because the charged cations and anions freely move around. Let's keep reading. Learning. While each reaction produces a different crystal made up of different elements, all ionic crystals have several similarities. Let's see what those are. First, each crystal is highly stable and non-reactive, okay? Indicating that all the atoms in the crystal have a full outer shell of valence electrons. This makes me think of octet rule. Octopus rule. Second, okay, so number 2. So number 1 was octet rule, basically. They're very stable. Each crystal is made up of 2 parts, a cation, that's positive, and an anion, that's negative. Since the crystals are made of 2 types of ions, they are called ionic crystals. Alright? Cations and anions are held firmly in place inside the ionic crystal by electrostatic attraction. I bet you that is a type of electromagnetic force, right? Because the electro part, it's just, come on. Electromagnetic. Okay, between positive and negative charges, opposites attract, right? Since positive cations are always next to negative anions, the crystal forms a regular pattern structure known as a crystalline lattice. I don't know what a lattice is, but I get the crystal part. So I'm just going to go with it. So crystalline lattice, okay. Third, so number 3, each crystal conducts electricity only when it's dissolved in water or melted. Okay, so conducts only when it's dissolved in water or melted. A compound will conduct electricity if a charged particle, such as an electron, cation, or anion, is free to move and carry an electric current. Okay, so stuff has to move to conduct electricity. When an ionic crystal is dissolved in water or melted, the cation and anion dissociate or break apart. Ha! I was right. Okay, so break apart means dissociate, which allows them to move freely and therefore conduct electricity. Solid ionic crystals do not conduct electricity because the cations and anions are locked in place in the crystal lattice structure. Okay, so crystal does not conduct. Alright, whether it's a crystal lattice or a crystal rose, it does not conduct. Okay, so here's this test for understanding part. Remember, we're going to do this in class, but if you're a mild student, you should definitely try this first. And I would recommend everyone to give it a shot, really. But give it a shot. Okay, and then let's keep reading once you're done with that. So you might want to pause it. Nomenclature. That's a big word. Okay, nomenclature. Naming ionic compounds. So this must have to do with naming. It's got an N. That contain group 1 or group 2. So I know group 1, group 2, those are up and down the periodic table. Metals is simple. The cation, which is the metal, okay, so the metal always loses electrons. Always comes first and the name is unchanged, so metal stays the same. Then the anion, which is the nonmetal, follows with an IDE replacing the last few letters of the element name. Okay, so if we have sodium and chlorine, we get sodium chloride. Alright, so there's the IDE, and that would be NaCl. Magnesium and oxygen, we get magnesium oxide. There's the IDE. The metal's unchanged, MgO. Calcium and bromine, we get calcium bromide, CaBr2. It's interesting, there's 2 here. I don't really know what that is. But I get the "ide" part. Okay, so this one you should be able to do. Give it a try. Let's keep reading. So ionic compounds that contain transition metals are a little more complicated. So transition metals, I remember that's the middle block. Because transition metals do not always give up the same number of electrons. I should have a comma. A Roman numeral is used to indicate how many electrons they lose. So basically, the Roman numeral is for their valence electrons. But I remember the valence electrons, we don't know how many there are. So I guess that's why we have to use the Roman numeral. Alright, so example, iron loses 2 electrons when bonding with oxygen. So then we would put a 2. So iron 2 oxide, and that would be FeO. Iron loses 3 electrons, so it's going to be iron 3. And there you go, iron 3. So 2 goes to 2 electrons, 3 goes with the 3 electrons. I get it. I still don't get the numbers here, though. The subscripts, oh, it's going to tell me. Great. So the subscripts, I know that's like a subscript would be like, this is the subscript. On the formula, indicate the ratio of metal to nonmetal atoms needed for both to achieve a full valence shell. Part 3 will demonstrate one way to determine this ratio. Alright, so I guess we'll find out later. But essentially, I guess this is saying there's 2 to 3. There's 2 to 3 for this. And here there's, I guess I'm going to assume 1 to 1. Here there's 1 to 2, 1 to 1, 1 to 1. Alright. Test your understanding. Okay, give these ones a try. We'll do them in class. I notice here they tell you how many electrons you have to assume, so that must be for the Roman numerals. Okay, last one. Part 3, reactions that produce ionic crystals. So based on your knowledge of ions, name each ionic compound, construct a drawing and description that accounts for the formation of each crystal below. Your model should clearly show the behavior of electrons and show how each atom gets a full shell, indicate the form of each compound. Whew, this looks like a lot. So we have beryllium reacts with chlorine. So I changed the chlorine to "ide." So beryllium chloride would be the compound. Before bonding, this is what the Lewis structure would look like. B would have 2. Chlorine would each have 7. During bonding, right, the metal loses electrons, so it's giving 1 to chlorine, 1 to chlorine. I guess there's 2 because if it just gives 1 away, the chlorine will be happening, but not the beryllium. So I guess that's why there needs to be 2. I'm getting the ratio now. Wow, that was exciting. Okay, yeah, so there needs to be more than 1 for this example. Okay, so then beryllium loses 2, so it becomes 2 plus. Chlorine gains 1 each, so it's -1. But then there's this right here, which I guess tells you how many atoms there are. So the subscript tells you how many atoms there are. So the formula is BeCl2. Be only has 1 atom, chlorine has 2. Let's read the description. So it says discuss electronegativity, electrons, ions, and the structure. So beryllium has a low electronegativity, check, whereas chlorine has a high electronegativity. Okie doke. I know that from my periodic trends. Beryllium will lose its 2 valence electrons, so now they're discussing electrons, forming a +2 cation. So now they're discussing ions. While 2 chlorine atoms each gain an electron, forming -1 ions. So they're doing electrons and ions. The two ions then attract each other through the electromagnetic force, forming a crystal lattice. That's the structure. Okay, so it seems like they've got each one of those. So you should be able to do something like this. If you know you're going to work a little slow, you should give a shot at the next one, which I think is sodium chloride. Exciting stuff. See you in class.